Hello, good people of the pathway. Mr. Klein here. And today in section 3.8, we're going to be talking about which test do I choose. Over the last couple of weeks, we've learned a number of different styles of hypothesis test. And the goal is that by the end of today, when you look at a new situation or a new set of data, you'll be able to identify which one of those tests is the appropriate one to perform to answer whatever question you're trying to answer. Now, I would organize them into two categories. There are one-column tests and there are two-column tests. Let's start with the one-column tests. The two one-column tests are very similar to each other. There is the z-test and the t-test. The z-test is going to look a little something like this. I'm going to give you a formula. Take the sample mean, subtract the hypothesized mean, and divide it by the population's standard deviation divided by the square root of n. And the t-test is going to look very similar. Same numerator. Take the sample mean, subtract the hypothesized mean, divide it by the sample standard deviation divided by the square root of n. So how do you distinguish whether you should be using this test or this test? It is determined by whether or not you have the population's standard deviation. Okay, so you're going to use this when the population standard deviation is known, and you're going to use this when the population standard deviation is unknown. Okay. And recall that when you're using a t-test, the shape of the distribution depends on how big your sample size is. Your degrees of freedom will always be equal to the sample size. Take away 1. And that a z-test is a stronger test. We do this if we can, because it will give us a lower p-value as opposed to the t-test, which has more room for error. Okay, so that's how you distinguish these. We kind of talked about that before. This distinction is maybe a little bit trickier. Suppose you have two columns of data. To see what I mean, let's just look quickly at our spreadsheets for tonight's assignment. First problem has one column of data. Second problem has one column of data. The next problem, you'll see that there are two different columns of data. So that's when you look at this kind of situation. Okay, so two column tests. You're either going to be looking at what we call a matched pairs t-test, or you're going to be looking at what we call a two-sample t-test. If it's the matched pairs test, you will know that it is matched pairs because the rows will form pairs. What do I mean by that? I mean that this number and this number in the row, they go together. They're the before and the after. Or, like this person is compared to their sibling, but they will go together. If that's the case, your degrees of freedom are going to be equal to n minus 1. And the formula that you're going to use is going to be basically identical to the t-test. The only difference that we need to keep in mind is that you will be calculating the differences of the value. So this will be the mean of the differences. For your hypothesized value, it will always be 0. Okay, and the reason for that, maybe I should make a little note, is that your null hypothesis is always going to be that the mean of the differences is 0. And then in the denominator here, this will be the standard deviation of the differences divided by the square root of n, where n is just your number of differences. Okay. Okay, maybe something worth noting here is that your alternative hypothesis, you want to cook up the differences so that they're positive. So you're always going to be testing this, or if it's two-tailed, you could be testing this, but you're shooting for positive values. And you decide whether you want to do before minus after or after minus before based on that. So there's the matched pairs test. Finally, that brings us to the two sample t-test. For the two sample t-test, you will know this because you will have two unpaired samples. This comes up most often for us in the medical establishment when we are comparing a treatment versus a placebo group, right? The treatment and the placebo groups are not paired together. They're just two separate groups of individuals that we've run an experiment on. Okay. The test statistic formula is a little more complicated here. You need to find the difference of the sample means and then divide it by this formula. And I should note that in this case, your degrees of freedom are going to be different too. It's the number of people in the first sample plus the number of people in the second sample, take away 2. All right, so there's our 4 formulas. I hope you wrote those down. Let's see if we can identify which one to use for a few different cases. So which test? We want to know if you can identify which test to use. Here we go. A little bit of background. We're going to be talking about fasting glucose level. Fasting glucose is when you fast for a period of time and then some blood is taken and we measure how many milligrams there are per deciliter of blood. Anything below 100 is considered to be a normal, not normal curve, but just normal in the world level of fasting glucose. First question, you take a sample of 20 people from a population and you measure their fasting glucose level. You want to know whether there is evidence that the average level in this population is normal, meaning below 100. I want you to tell me, what test should you use? What should be your alternative hypothesis? What kind of study is this? And now for the answers. This is a t-test because we do not know the population's standard deviation, and we have one column of data. Your degrees of freedom are 19 because it is one smaller than the sample size of 20. Your alternative hypothesis should be that the population mean is below 100 milligrams per deciliter. And this is a population survey. It's not a cohort study because we're not following people over time. And it's not an experiment because we did not impose any sort of treatment on them. Question 2. You take a sample of 20 people from a population and measure their fasting glucose level. This time, you know that the population standard deviation is 10 milligrams per deciliter. You want to know whether there's evidence that the average level in this population is normal. Just one question this time. What test should we use? And this one is a z-test because we know the population standard deviation. On to number 3. You take a sample of 20 people from a population and measure their fasting glucose level before and after a medication. You want to know if the medication will lower their fasting glucose level. What test should you use? What should be your alternative hypothesis? What kind of study is this? Okay, answer times. This is a paired t-test. You have two columns of data, the glucose level before and the glucose level after, and they are paired together because the row would represent one person. You get 19 degrees of freedom. Your alternative hypothesis should be that the mean of the differences is positive, where the difference is before minus after. We want the after to be lower, so before minus after would be a positive number. What kind of study is this? This is a quasi-experimental design. It's an experiment because the diet is a treatment that you're imposing on people, but we don't have a placebo group to compare them to. So it's not a clinical trial. Last one for today. You take a sample of 20 people from a population. They receive a half of them receive a medication. The other half receive a placebo. You measure their fasting glucose level before and after a medication. You want to know if the medication will lower their fasting glucose. What test should you use? What should be your alternative hypothesis? What kind of a study is this? All right, answers, everybody. This is a two-sample t-test. You have 18 degrees of freedom because it is 10 plus 10. There's 10 in each one of your groups, minus 2. 10 plus 10 minus 2 is 18. The reason it's a two-sample t-test, even though you've got a before and an after, is that when you're all done, you're going to have two separate groups to compare. You're going to have the medication group, and you're going to have the placebo group. Oh, popped them both up. Let's talk about them together. So your alternative hypothesis is going to be that the mean of the medication population minus the mean of the placebo population is positive, or in other words, the medication has a greater effect than the placebo does. And finally, last but not least, this is a clinical trial because it meets all the conditions for a clinical trial, including that you have an experimental or a treatment group and a placebo group.